Good afternoon, girls violets. Today we'll be talking about batteries that are used to power your drone. What is a battery? A battery is shown in this very simple diagram. It consists of two different metals that have to be different metals, which I'll explain momentarily. And they're immersed in a liquid electrolyte. That electrolyte has some conduction ions in it, so it's not all ions. It's not a pure insulator. It's somewhere in between. And those electrodes create a voltage that can then drive current through a load. So that's what a battery is. Now, this is not a physics class. This is not a chemistry class. This is not a material science class. It's not even an electrical engineering circuits class. It's a drone class, but I want you to understand the basics so you know how to use batteries and safely deploy them. This applies not just to drones, but to all batteries. So it's going to be important if you don't know it to understand the difference between series and parallel addition of circuits. And it's going to be important to know what voltage, current, and power are. So let's start by just reviewing. I'll have 3 written slides and then the rest are all PowerPoint slides. So what is current? What is current? Feel free to shout it out.
Flow of electrons.
Flow of electrons. Technically, it's flow of charge per time across a surface that you define. So if you define some surface, let's make it 3-dimensional, just for fun. If I can, so there's a 3-dimensional surface. An electron, is a point particle. I usually like to draw the blue for no reason at all. So an electron is a point particle. It has charge of 1.6 times 10 to the minus 19 coulombs. And when it flows across the boundary, charge moves across that boundary. So current is defined as charge per time that crosses the boundary. Each electron has 1.6 times 10 to the minus 19th coulombs. So you add up the total amount of electrons per time, and that gives you the current. So it's a physical flow of electrons. Usually metals have 3 electrons in them that can move around. So charge is coulombs, time is seconds, and that has the units of amps. So that's pretty simple. The next question is, what is voltage? What is voltage? This is covered in EECS 180A. This should be covered in EECS 70A in Physics 7 series. So what is voltage? Not energy. Potential difference. So it's a little more subtle. I'm gonna be vague initially. So EECS 178A will give you the mathematical definition. But we're gonna just go quickly through it. So it's the force that pushes electrons, okay? So in order to get electrons to flow in a wire, you have to have some force on them. If there's no force, they're going to stay still. There'll be no current. So voltage is like the force that pushes the electrons through the wire. Okay. And that's all you need to know mostly for this class. So the symbol is V or delta V, potential difference, and the units are volts. The unit is, the name of the unit is the same as the name of the object. Whereas current is called current, unit is amps, voltage is called voltage, and unit is volts. So the more the force, the more the current. So if you have more voltage, you have more current. And that's basically all you need to know as a drone pilot. There's one more small quantity you need to know, which is power, which we don't do much power calculation in this course, but just for completeness, it's the current times the voltage. It has units of watts, which is equal to joules per second. Okay. Now, a battery generates a voltage. How does a battery work? So we need to talk a little bit about solid state physics. So I have one slide on solid state physics. So consider two metals, metal 1 and metal 2, and consider the energies the electrons have in that metal. There's many, many electrons in that metal. There's 10 to the 23rd electrons in that metal. They can't all have the same energy because of the Pauli exclusion principle. It says two electrons cannot occupy the same state at the same time. And the Nobel Prize was given for quantum mechanics a couple days ago. So yet again, quantum mechanics shows that it's important in modern society. So the electrons have many different energies. Each electron has a different energy and they're distributed. Okay. And they're distributed up to some maximum, which is called the Fermi energy. So anything above that, there are no electrons, but all the states below that, there are electrons that have that energy. So these states, the electrons have these energies, okay? Now metal 2, it's similar. We can ask, what are the energies of the electrons in metal 2? And the answer is the same. They don't have the same, they don't have the same energy because of the Pauli exclusion principle. They have to have a distribution of different energies. So each electron is a slightly different energy. And they're all the energy levels are full up to the Fermi energy of metal 2. But and then one key result is that E Fermi depends on the number of electrons per meter cube. So it doesn't depend on the total number of electrons, it actually depends on the density of electrons. So different metals have different density. So different metals have different Fermi energy. So that's solid state physics 101. Now, what happens if I bring those two metals together and have them touch is that these electrons here want to go over to these empty states here. So if we bring those two metals together that have different Fermi energies, the electrons from the higher Fermi energy metal will move over to the electrons from the lower Fermi energy metal, and we'll have current flow. A lot of current. Too much current. So instead, what we do is we don't bring them together to touch, but we put them in a beaker. So we put both pieces of metal in a beaker, and then we immerse the metal in liquid. So both metals are immersed in a liquid. Now, the liquid, if it's insulating, nothing happens because it's an insulator. It's as if there was air or vacuum between those two pieces of metal. Instead, we put a small concentration of ions, for example, lithium, that are allowed to move around freely in that liquid. They're positively charged atoms. And when that ion gets close to an electrode on one side, an electron can come onto that ion. Now that ion becomes one less charge, and then that ion diffuses around, it moves. The ion moves. It doesn't go in a straight line because it's bouncing off of all the other atoms. And so it diffuses, which is slow, which is exactly what we want to do. We want to slow down the transfer of charge from one to the other. And eventually the ion gets to the other side. It has that extra electron on it. And it deposits that electron onto the other metal. So if the metals are identical, that happens in both directions with equal rates. But if the metals are different, then on average, more electrons are getting moved in one direction than the other. So with different metals, with different work functions, we have current flowing from one of the metals to the other metal. So you want a lot of ions, but you don't want just one electron, you don't want just one ion, you want many, many ions per time doing this process. Eventually, the electrons can stop there, and so then the voltage, then the current stops, or you could put a wire. Let's make the wire, and put a resistor here. So you could put a wire, and those electrons that get brought from one side to the other then will go up through the wire, through the resistor, and go back to the original electrode. One's called the cathode, one's called the anode. That closes the circuit, and current can flow. So that's all that a battery is from a scientific point of view. Questions? Good. Now, if it's very difficult to predict the behavior of batteries directly, so most battery technology is experimental. This is the theory, but in the end, you do what Thomas and Edison did with a light bulb, is you just experiment with many different materials. You use as much scientific theories you have from chemistry and physics, but ultimately you have to do experiments to make sure everything's going to work, and you might discover new things. So that concept can be used for any material and any electrolyte, and maybe you students will go out and invent a new kind of battery, because certainly we need better batteries. I think that much is clear. But we have what we have, and we want to play our own, so we're going to use existing batteries. Now, there's an analogy, the last slide is there's an analogy with water. Analogy with water. That's going to help you, I think, when you're flying drones. So consider a beaker that has water in it and another beaker that has water in it. And they're filled up to different levels. This one is filled up with a lot of water. This one's a lower level. Now, there's no water flow from one to the other. We're just talking about water now, okay? Forget about all the quantum mechanics, just pure water. And you have a glass of water on the sink and another glass of water in the sink, and each has a different amount of water in it. So there's no water going from one to the other. So if we were to make a tiny little hole here and put a straw between them, what's going to happen? Water is going to flow. And it'll flow from the one side to the other. So water will flow. So eventually enough water flows that the levels of water are equal. So then no more water will flow. So that's the same thing that happens in a battery. Initially, the battery has more electrons on one side than the other. You allow them to flow through, eventually it balances out, and you don't have any more charge. So what would you want to do then? You'd want to fill one glass with some more water from the sink to charge it back up again. So that's what you'll be doing when you're flying your drones. Fly the drone, gets more and more level, and then when you're done flying, you pump it back up again. So in this analogy, the current electrical is analogous to the flow of water. And the voltage is analogous to the change in voltage, if you want, is the change in pressure. So the reason the water flows is that there's more pressure on the water in the left side of the straw than the right side because there's more water on top of it. So the absolute height of the two waters doesn't matter. It's the difference in the heights of the waters that determines how much current flows or water flows. So that's the change in pressure. There's a little more pressure on the left hand than the right hand side because there's a little more water on top of it. Both of the ends of the straw have pressure on them because there's water pushing down from gravity, but the one on the left has a little more pressure than the one on the right. And then, of course, the resistance to flow, if you really want to push that analogy, is how thin the straw is. Okay. So if the straw is really, really thin, there won't be much water flowing. Eventually, it's going to be equalized. But if the straw is really, really thick, a lot of water will flow. Okay, so that's the resistor in the current. So that's the analogy to think about batteries. And the rest of it is basically, quote unquote, just experiment. So the lithium ion battery is the most important one, which got the Nobel Prize in chemistry. And they don't use metal and water. So they experimented over the course of many, many decades about different kinds of materials to use. So the Nobel Prize in 2019 has a really nice set of pictures of the experiments they do. I'm going to summarize them quickly. The link is there. You can read it. And I want to summarize it for the purposes of this class. So they're using lithium as the ion that moves electrons back and forth. Lithium is the shuttle that's dissolved in the liquid. Okay, and it's very light because it's only number 3 on the periodic table. And there's a periodic table for you if you want to know. So, and it's very reactive, so it can easily accept and donate electrons. You don't want an inert atom because it's going to just sit around and do nothing. You want an atom that's chemically very reactive. So the very first experiments done by one of the 3 Nobel Prize winners used a cathode that was a metal, we don't care what it is, but they used an anode that was actually metallic lithium. And metallic lithium is extremely reactive. So it's very, very dangerous. In fact, he was very, they had a lot of fires in his lab. And they did get it to work, but it was too dangerous to be used in modern consumer electronics. And it only produced 2 volts. So another problem they had was that the metallic lithium, as you used it, grew these whiskers and eventually short-circuited the battery. So the next step they used was carbon electrode instead of lithium electrode. So there's no lithium electrodes, there's only lithium dissolved in the electrolyte, but there's 2 different electrodes. They're not exactly metals, but they're conductors, and that gave them 4 volts. And that gave the Nobel Prize in chemistry. Okay, so that's a brief story of how they discovered lithium ion battery. So it's called a lithium ion battery because the lithium atoms are the ions in the solution that carry charge from one electrode to the other electrode, and then they diffuse back and carry it again. If you want to know more, I'm going to link a really good video here. Let's see if I can play a little of it. Oh, there's a yeah. So this is a 30-minute video that just came out and I watched it. It seems to be correct. So it's a what is it? It's a well, 30 minutes. Well, hey, everybody likes coffee. What? Skip? Okay. So they show the history of it and they even show what it looks like unrolled. Okay. So feel free to watch that video in the privacy of your own home. And they talk about the story of the discovery of the lithium ion battery. So lithium ion battery is not the only game in town. There's lead acid, which is used in your car. There's nickel cadmium. There's nickel metal hydride. There's others that aren't plotted on here. Here's the reference to this paper. I always try to provide primary source references for all the information I provide instead of just verbal. So the initial lithium metal one, the lithium metal was the electrode, and it's very unsafe. So they had to solve that problem before it was possible to use it safely. And that the reason they got the Nobel Prize in chemistry in 2019 is that enabled the wireless revolution. Cell phones, laptops, iPads, everything. But prior to that, the battery technology was too heavy and too low energy capacity. So the very first cell phones from the 80s had a huge brick, and that was all battery. So that was a Nobel Prize that was about a technology that really did change the world. So it also allowed drones. So we'll be using lithium-ion batteries in this class. Now, let's talk a little bit more in detail about lithium-ion batteries. First of all, there's a couple different versions of them. The simplest one is called LiPo, lithium polymer. So instead of having a liquid with lithium ions in between the cathode and the anode, and in this case, they're showing aluminum copper, it's also possible to use other metals, okay? As long as they're two different metals, it becomes very empirical which ones work the best. So here they have a liquid between them, but instead of having a liquid, they have a polymer gel. So lithium polymer batteries have a polymer gel in between the electrodes. They're called LiPo for short. It means lithium polymer. And this is a picture of what a modern lithium polymer battery looks like. You might even have one of these in your cell phone. So there's the anode, there's a cathode, and there's a separation layer, which is the polymer. And then there's a fluid in there inside the polymer to make the ions able to go from one side to the other. And then you have the lithium ions in there. And then that entire thing has to be protected, and usually it's protected in a foil pouch, and then you bring out the two electrodes. They come in all shapes and sizes. And you can pretty much decide what shape and size you want, and you can probably find a place to sell them. This one is a smooth. And there's your wires coming out. Now, for drones, we want them very lightweight, so we do not have a protective case around them. These ones I'm showing you don't have a protective case around. So be careful. There's a second kind called lithium-ion battery. Now, I didn't invent the nomenclature, but the difference is mainly it's a cylinder, not rectilinear, and there's no polymer. It's actually a liquid between cathode and the anode. Other than that, you're still using lithium as the shuttle of charge from cathode to anode. And usually the materials are similar for the cathode and the anode. So that's lithium-ion battery. So you have LiPo, and you have, sometimes they call it Li-ion, like a lion, okay? These are the short versions for it. One is square, one cylinder, one has a gel, one has liquid. The one nice thing about the cylindrical ones is that they are also encased in a hard steel shell typically. So one more difference is lithium-ion usually has a metal case. And you can get more surface area also. That's another advantage of the Swiss bowl design, okay? So if you want the same surface area for a LiPo, you have to have a very large sheet. So here you're rolling it all up. You get much more surface area, so you get more current capacity or charge storage capacity. So they are also typically encapsulated in a metal casing. And these are the batteries you use for your RC controller. So whereas LiPos come in all shapes and sizes, lithium-ion batteries come in only a few. There's 18650, there's 21700, there's a smaller one that's almost never used, but almost all of them are this size, and I'll show you a few examples in a minute. But the reason it's called 18650 is because of the dimensions here. Now okay, so what's next? So they're very cheap. You can, they're a few dollars each. And that's light bulb. Okay, but Professor Burke, what about the electrical properties? Because that's the most important thing. What's the voltage? What's the current? What's the power? How long can I fly my drone? How long can I talk to my friends on Facebook, Snapchat, YouTube, Instagram? How long can I surf the internet on my laptop before the battery dies? So those are all things that we're going to answer in the next part of this lecture. But first, let's talk about safety. So, does anybody know what this is? What?
Exactly.
Yeah, Hindenburg, what happened? Yeah, why? Yes, it was filled with hydrogen. So, interesting story. US has the world's biggest reserve of helium gas. You look over there at the periodic table, helium is in a noble gas, so it's not reactive. So helium is what is used in birthday party balloons and so on, and in blimps. But the US and Germany were not on good terms during World War II. So, and before World War II. So the US refused to sell its helium to Germany. So instead, Germany used hydrogen because hydrogen is very plentiful. It's in the ocean because H2O. So you just have to split it. So they use hydrogen, but hydrogen is also extremely reactive. And what happened is, but it's light. So it's great for aerospace engineering applications, but it's extremely reactive and inflammable. So what happened is it flew from Germany to New York City. They were about to connect it to this mooring station, and there was a spark because of static electricity, and the rest is history. We don't want that for our drones. So lithium is also extremely reactive. If you look, it's also very reactive. That's good and bad. It's good for the battery function, but it's bad for the safety. So if you use pure lithium as the metal electrode, the lithium itself will burn. But since we're not using lithium electrodes, we're only using lithium ions in the electrolyte. Typical lithium battery fires, I think, are not just lithium reacting, but also the electrolyte itself may be flammable, the electrodes may be flammable, and the energy that you store it's extremely high energy density. So the most likely form of initiating a lithium polymer battery fire is a microscopic short circuit. So that's why in this YouTube video, they say, I like this picture. Bad idea to put a pin on there. So what would happen is if you put a pin through that foil, you're letting a lot of air in, which could be used as, when a fire starts, it can use that oxygen to burn. But you also short circuit the cathode to the anode, and that drives a lot of current very, very quickly. And that current then will melt the cathode, the anode, and the electrolyte. And it will draw more current, and you have a positive feedback loop. And everybody knows a positive feedback loop is not stable. So you have thermal runaway, and the instantaneous rate of increase in temperature is 100 degrees Celsius per second. So you can do the math on that, and it results in a fire. So we don't want that. So I have a couple fire videos to demonstrate that. And we may need me. Let me see. One. Oh, we didn't punch it, okay? We didn't touch it. It's sitting there charging. So the other way that you can cause a fire is by charging it up incorrectly.
Okay. Yeah, John.
Okay, so don't be that guy, so to speak. But wait, there's more, because I think I have 3 of them here. This is another one, we're not gonna watch the whole thing.
This little guy do?
Let's find where it blows up, because it always people. So here it's inside of the bag, but you're still charging it correctly.
Oh my god, oh my god, oh my god.
And just spontaneously ignited.
You have a little tiny battery and that kind of lipos?
That's another one. Let's see what this is. This one, they're charging it. Like this is the bigger one.
Oh, whoa. Holy moly.
So
Oh my god, they're going
even a fireproof bag, it's not really fireproof, okay? It's fire resistant. So, yeah, that's that one. And I think I have one more example. Which is yet another video. They're all over YouTube.
Sure sign that bad things are happening. If you hear this, when you're charging, get the battery off the charger and get it outside as soon as possible. Oh, it's gonna go. It's gonna go. There it goes. I hear the hiss. I hear the hissing. This is the end. It's probably, I smell it. I can smell the fruity smell. The end is there. Oh, there's the psst. There's
Okay, that's enough of that. So be careful. The it's not just little tiny ones that go up in flames. So in 2010, UPS Flight 6 was lost. Both crew members lost their lives. The 747 exploded, and they don't know the cause of the fire, but it had, according to this report, 81,000 lithium batteries in the cargo hold. So ever since then, the FAA has not allowed lithium batteries to be shipped by air. So if you buy batteries, they're shipped by ground. And it may be, I don't know, that one of those batteries spontaneously caught fire and then just it spread to all the other 81,000 batteries. So also, when you travel, don't put your lithium batteries in the checked bag. Laptops, cell phones, etc., carry them on. And once a week, on average, there's a lithium battery fire in an airliner somewhere in the world. And if it's in the cabin, the flight attendants can put the fire out quickly enough that the airplane can safely land. But if it's in the cargo hold, there is a fire suppression system in the cargo hold, but it may not be, it may not function. You don't want to rely on that. So don't check batteries in your check bags, bring them in the carry-on, and flight attendants are trained to deal with lithium battery fires. So why is it so safe? It's so safe because a lot of your batteries are mechanically protected in your laptops and your cell phones. There's a steel case around them. So the chances of a pin puncturing it are very low. And they also are charged with chargers designed just for that device. But we have drones. So we don't want a steel case around our batteries because that adds weight. So we just have, for our LiPo batteries, aluminum foil. So that's very fragile. And sometimes the drones crash hard. So it's possible to have a drone crash, and if it's hard enough crash, it'll damage the lithium polymer battery, it'll create a fire. It's so if that happens, it's very difficult to put the fire out because it's a thermal runaway. The electrodes themselves have oxygen in them that they release. So even if you pour water on it, there's still oxygen from the electrodes, which are metal oxide electrodes. Another thing is if the lithium polymer battery starts on fire, if it's more than one cell, the first cell may burn and the second two haven't gone off yet. So you may think it's gone, but then it'll flare up again. And so it's very hard to put it out. So if there's a fire, don't try to put the lithium battery fire out. If you have to fight the fire, the only thing you can do is contain the fire around it. Make sure that it doesn't spread. When we fly at the Ark, we fly over very short grass, which I don't think will spread. If you lit the grass on fire with gasoline, I don't think it would spread very quickly. Well, maybe if the whole thing was covered in gas, but if your drone crashes at the Ark and the grass is very thin, I don't think it's going to light the grass on fire. However, if you crash in tall grass, it will. So that's why one of the reasons we fly at the Ark, it's much safer. And keep that in mind when you graduate, where you fly, especially in Southern California. There's a lot of tall, dry grass around here. And indoors, it also emits a lot of toxic fumes that are very dangerous for your health. So my advice is if it goes off indoors, call 911 and, pull the fire alarm, immediately evacuate the area and call 911. And, but my other advice is prevent it from happening in the first place by properly charging it. And also, okay, we have a question. That's good. We should have a lot of them. When you charge it, never, ever, ever charge it unattended. You always hear something your parents say, don't run and carry something at the same time. This is a real thing. Don't ever do it. Never, ever, period, the end. No exception. Don't ever charge a battery unattended. That's all I can say. And there's lots and lots of stories of people with drones that charge, and especially drones that charge their batteries unattended, and they aren't home, and they come home, their entire house is burning. So the other thing is, it would be very wise to leave a buffer zone around it so that there's not flammable materials very near it. So in case it does start, the battery goes on fire, that the fire doesn't immediately spread to some really flammable materials right around it. What's your question?
Yeah, I was gonna say, if like the worst case scenario happens and your battery lights on fire in the drone cage, I'm guessing, is that flammable material in there, or what would happen? Should we call 911 still then?
In general, yes. That's the default. Okay. The drone cage is on concrete, so I don't think that's flammable. And the cage itself is a net, which probably is a little bit flammable. And that's a good point. We should have a fire extinguisher there just in case. So when in doubt, just call 911 and we'll work out the consequences later. Okay. The fire department will be much happier if you call them than if you don't. And that's a common thing with LiPo batteries. Apparently, I have some literature that I'll reference where people try to fight the fire first, then they call 911. And those few minutes are critical for the fire department. Fire department comes to UCI every day. They usually it's something very trivial. So it'd be better to have them come than not. And the honest answer is if you crash the drone in the drone cage and there's a LiPo fire and the fire department comes, I don't think that there will be anything burning more than the battery, okay? But once a fire starts, really it's better to have the fire department make that decision, not you. In the lab, if it happens, just pull the fire alarm and get everyone out. If you pull the fire alarm, that'll also trigger the fire department to come. Yes. That's a good idea. I should ask for that. We don't have sand. You can. I don't advise that you try to fight the fire. Okay, this is a recorded video, it's gonna go to the public, but it's also for you as students. If you're not certified in firefighting training, I would advise don't try to fight the fire. Certified firefighters can use water, they can use fire extinguishers, they can use sand to put it out. But even immersed in sand, once, I can tell you this from the laws of physics and chemistry, if you have a lipo fire and you immerse it in sand, it will still burn. And even if no oxygen comes in, the electrodes themselves are generating oxygen that will fuel the fire. So it's very, very difficult, even for professional firefighters, to put out a lipo fire once it starts. But I don't advise you to try. And yeah. So if one starts in our lab, our benches probably won't catch on fire right away because they're very thick metal. And the oscilloscopes next to it probably won't. But you know, don't have lots of flammable stuff right next to it. And then in the drone cage, there's not really anything flammable there. And then out of the arc, the grass is very, very short. That's very well maintained and that's somewhat flammable. But we always have fire extinguishers just in case you want to put the fire out around it. But you can't really fight the fire itself. It's best to prevent it. That's why I'm giving this whole lecture. So the way you prevent it is don't puncture it and charge it correctly. Yeah. Okay. What other things do we want to discuss on this? Oh, so I have some links here to firefighting associations that give you more information. So you can fact check me. You don't have to take my word for it. These are reputable organizations. I put up on the Canvas page, and it's linked here. Lots and lots of references that you can go and read about it. And actually, the way the fire starts, it progresses and is put out is still a research topic. That means it, you know, there's still more research that could be done to improve the safety of the batteries and the firefighting ability of firefighters. So it's something that you have to be aware of. Other questions? Let's see, where do we go on the, okay, so charging and safety are very important. Take good mechanical care of your batteries, take good electrical care of your batteries. And by the way, I'm treating you as engineer students. So you can buy lots of different kinds of batteries and you can charge them all with lots of different kinds of chargers. So with a laptop, you don't have a choice. You can only use the battery that was designed for that laptop. And with a cell phone, you don't have a choice. You can only use the battery charger that was designed for that cell phone. But we are tinkerers and we're building from scratch flying vehicles. So every gram of weight counts for us. And it's a teaching class. So we don't have all those safety mechanisms built into our drones. And in general, it's a trade-off, just like everything in engineering, between a perfectly safe drone and one that's very lightweight. And if you ever build and design any, including after you graduate or during this class, you're going to have to make that trade-off. And I've made that trade-off when I designed it for you, because I could have made it safer by putting a lot more protection around the batteries, but then it would have been a lot heavier. And at some point it wouldn't even fly. So there's nothing that's perfectly safe. The other thing is about disposal. If you have a puffy battery, dispose of it. But obviously don't throw the battery in the trash because it might light the trash can on fire. And so at UC Irvine, there's environmental health and safety, and they will dispose of it. You just call them on the phone. The phone number's in the lab. It's probably in the back of the building here. I mean, here's the thing about emergency. So it's a real emergency, call 911. But there should be a phone number on here for EH&S, environmental health and safety. They'll come and pick it up and they will dispose of it properly. Once you graduate from UCI, if you still live in Irvine, City of Irvine has a hazardous waste dump down by the train station. And it's free for all Irvine residents. And you can bring any hazardous waste there within reason, not huge amount, but it's household, it's meant for households. And the way it works is you pull in. They ask you to roll your window down, they say, what do you have? You say lithium-ion batteries, or I have paint. And they say, okay, pop the trunk. You pop the trunk, they take it out of your trunk, they close your trunk and you drive away. Free. And then they handle the disposal. I don't recommend doing disposal yourself. I recommend having it done by a professional, which is not just putting it in the trash can. Okay. And then if you live in a different city, there will be a similar arrangement. Let's see. So don't poke them with a nail. Don't charge them incorrectly. And when you are charging them, make sure you're always there, and you should store them in an intelligent, safe way. Yes.
If you have a battery that hasn't been charged or used for like, say 6 years,
Yes.
should you dispose of it, or could you still?
The question is, okay, so the question is, if you have a 6-year-old battery, should you dispose of it? And the answer is it depends. It might still be perfectly functional. And I'll show you in a bit if you can ask again. So there's no short answer to that question. If it's puffy, I would recommend you dispose of it, because that means that air has formed in the inside of it. It's mechanically less stable, and I would just dispose of it. And it also doesn't last long time. But if you have a 6-year-old battery that's been charged at storage charge, and it's been, it hasn't been abused by being at a high temperature, then it probably still is okay to use. But you need to check the voltages of the electrodes. And be more careful than, always be careful. And if there's a permanent shelf life, I don't know. Actually, I don't know the answer to that. Like if it's a 1,000-year-old battery, does it not work? Probably not, but I don't know what the spec is on the shelf life. Well, you'll see that if you're using them, usually they'll get worn down, because you can only recharge them 500 times, and then they lose their abilities to get recharged. So it's unusual, but that did happen to me once. I had a battery for my Samsung phone, and we moved labs, and I found it, and it was puffed up. And I called the H&S, and they came immediately. They're really good. They came. It was at 5 o'clock on a Friday afternoon, and the officer drove all the way back home from Riverside. It was an hour drive. He came just for that battery. He put it in his battery safe, explosion proof bunker for the weekend, and then they disposed of it on Monday. So they will come and get your batteries for you at UCI. They're very careful and dedicated. But if you do it intelligently, you can use it, because everybody in the room has probably several batteries on them. Their laptop battery, the iPad battery, the cell phone battery. But if you're doing it with drone batteries, there's no casing, you need to be careful. Okay, so it's not only safety, but what does it do electrically? So we have about a half hour left to get through all the electrical stuff, which is quite a bit. So this is an ideal battery. It creates a constant voltage until it runs out, and then the voltage drops to 0. And that's what a power supply is in circuits. It creates a voltage no matter how much current is flowing. And that's not what any battery is. But let's talk about the capacity. So this is time in fully discharged. What does that mean? So it's like the water analogy. When you have 2 cups of water and all the water has flowed from one side to the other, you're discharged. So let's go back to that picture. So here, it's the total amount of water that has flown from one side to the other that determines if this circuit is discharged. It doesn't matter whether the water flows slowly for a long time or all at once or little by little. So it's the integral of the flow dP, which is the total water that is transferred from left to right, okay? So when that integral equals the difference in the volume, then you're done. So you need to integrate the flow dt to find out whether it's discharged. So you can, and you could even have a little valve here that you open and close. And you could close it for a while and then you open it later. So it doesn't matter what's going on instantly, it's the history of the total flow integrated over time that gives you the total amount of water. And it's the same thing with the capacity of batteries. So an ideal battery will allow you to flow current at a constant voltage up until you've used up all the current. And that capacity is called the capacity. It's the integral of IDT. Okay, so if you use a lot of current, it won't last as long as if you use a small amount of current. And that's the quantity that determines. And it's measured in units. I is amp and T is hour. So the unit is amp hour, or typically they say milliamp hour, okay? So your batteries have a capacity of 2200 milliamp hours. That means you could run your battery, and it's listed on here, big letters. You could run your battery at 2.2 amps for 1 hour, and then you're out. So if you run it at 4.4 amps, then you're out in 30 minutes. If you run it at 0.22 amps, then you're out in 10 hours. So pop quiz, what if you run your battery at 10 amps, how long until you run out?
A little bit more than
Right.
Yeah.
So it's something like 15 minutes. But we can do the calculation if you want. So it's 2.2 amp hours is equal to 10 amps times your time T. So it's 2.2 amp hours divided by 10 amps in hours. So it's 0.22 hours. Okay, so about 15-20 minutes. So your drones cruise at 8 amps. So that's about what your flight time is going to be. So that's the capacity. The next important spec is the max current. So there's a maximum amount of current that you can carry. You can't have an infinite current. So it would be nice on there if they just said I max equals so and so many amps, but that's not the way they spec it. They spec it as I max is equal to the C rating, which in this case is 50C. So you have to multiply that by the 2.2 amps. So in our case, it's 104, well, let's say it's 2 amp hours. It would be 100 amps. So the maximum current that we can have from our battery is 100 amps, no more. And then it just will stop. So if you short circuit it, the current goes to infinity mathematically. So if you short circuit, it will go up to 100 amps and it won't provide anymore. So that's called the C rating. So you need to worry about that, because if that C rating doesn't allow you to give enough current to fly your drone, it won't work. So our C rating is 50C. That means we get 10 amp. We can get 100 amps out. We can cruise at 10 amps. Even if you punch out, you're probably gonna use 20 amps. And so that's fine. These we'll talk about in a moment. And then there's of course the weight, which is 98 grams. So your drone is 250 grams. So that's a significant fraction of the weight. So instead of time, we put the discharge current here, integral of IDT. Now this is that was an ideal one. This is a real one. And this is a very important curve. So let's go through it closely. First of all, LiPos at full voltage are 4.2 volts. So if you charge up all the way, it's 4.2 volts. And if it's totally discharged, it goes all the way down to 0. But it's not just a square curve. This black one is an actual measured curve of what the voltage is as you discharge it. So this is equal to the integral of IDT over the capacity in milliamp hours. Okay, so it's the total percentage of integral of IDT that you've used. So the black one is showing that it starts at 4.2 volts initially, and it actually goes down very quickly to under 4 volts. And then it stays pretty constant for a while. And then when you have about 10% left, it's at 3.6 volts. So if it's at 3.6 volts, you have 10% left, you better land. Okay, so however, there's not just a black curve. 0.2C means we're running it at 0.2 times the capacity rating. So for our batteries, that would be 0.2 times 2 amps. So that would be 0.4 amps. So if we run our battery at 0.4 amps, we get the black curve. However, when we fly, we run our batteries at 8 amps because in flight it's about 8 amps. I didn't calculate it, I just measured it. You're going to see it on your display. ArduPilot calculates it based on the voltage drop across the 50 ohm resistor on your flight controller. So not all flight controllers measure the current, but ours does. So if you're running it at 2C, which would be 4 amps, then you get the green curve. So the discharge curve depends on how much current you're drawing. And so now a typical flight profile will be you go here, you take off, and you start to use some battery, and then you land, and then you go back to zero current. So when you're in the air, the discharge curve is this green one, but when you're on the ground, the discharge curve is the black one. So what'll happen is it'll be 4.2 volts, you take off, it's immediately going to sag to under 4 volts, even if you've only used a few percent. And then if you land immediately, you only fly for a few seconds, then it's going to go all the way back up to about 4.1 volts. So there's voltage under load, it's going to be much lower than the voltage when it's not drawing any current. So for this reason, the discharge curve is, the voltage of the battery is not a good measure of how much gas you have left in the tank. And ArduPilot will actually integrate the current for you. So ArduPilot, if you have a current meter, which we do, will integrate in the computer, onboard flight computer, the amount of current times time that you've used, and that'll give you an indication. So there's a discharge curve that will convert voltage to percentage. And here's a table of it. And this meter that you have in your kit has that discharge curve programmed in. So that's a very convenient meter that we'll use here in a few minutes. Okay, now the other kind of battery is a lithium ion battery, which is similar, but it has a different discharge curve. And it actually is very, very flat for a long, long, long time. Okay, so that's a very, very different discharge curve. And here's another discharge curve. And now let's talk about the specs. So the 18650 is a very important battery. This is an example one. And they actually, the manufacturer gives you the discharge curve for that exact model of battery. And I never used to believe it, but I believe it now because I measured it. So these discharge curves from manufacturer are very reliable. So if you want to know for a particular battery, you get the discharge curve, you can count on that in your designs. So the conclusion is if you're running a LiPo and you're 3.7 volts under no load, stop flying. If you're running lithium ion, if you're 3.0 under volts, stop flying. Or you can time it. Now the other thing is like you asked about the age. So every time you go through a charge discharge cycle, you lose a little bit of capacity. So you lose about 50 milliamp hours every time you charge discharge a lithium ion. So if you charge discharge at 300 times, you're going to lose 10 or 20% of the charging capacity. And this also goes through for laptops, for cell phones, everything. Actually, none of this is drone specific. This is for all lithium batteries. Okay, next topic is series and parallel. So let's say you buy 2 batteries and you want more voltage than 4 volts to drive your circuits. So actually 4 volts isn't enough, right? Because most computers run at 5 volts. And, you know, maybe you want a 12 volt power supply for some other radio or something. So you could put them in series and then they'll give you twice the voltage. So this is called a 2S configuration. So if each one of these is 4 volts, what's the total voltage? 8 volts. And you can go up to NS. You can go N is greater than 1 and less than infinity. Now, but each one can only have a certain amount of current. You can also put them in parallel. So if this is 4 volts and this is 4 volts, what is that? 4 volts to the same voltage. but the difference is you can have more current capacity. So if this one can take, let's say 100 amps, because it's quote unquote C rating, that's how much current it can have. So let's say IMAX. So if this one has an IMAX of 100 amps and this one has an IMAX of 100 amps, what's IMAX of the pack? 200 amps. And so on. So this is called 2P for parallel. So P can be greater than 1 less than infinity. So then generally you have something S, something P. Your battery is 2S, 1P for this class. It's 2 in series, 1 in parallel. So you get 8 volts out when it's charged. But you can build up all sorts of them. Here's a lithium ion pack that has 3 by 2, so that's probably a 3S 2P and so on. Here's one that's 6S by I don't know what P. 6S something P, I don't know how many are in parallel. You can also do it with the lithium polymer ones. So this is a 6S LiPo. So it's 6 of them in series, so they're stacked up. So yours, there's 2 of them in series. So you have to have one wire on one side of one pack and one on the other, and then the entire thing is shrink wrapped in plastic. And so on. So Tesla, a very interesting case because they decided to use 18650s, a very wise engineering and business decision in my personal and professional opinion. Because before Tesla, the big manufacturers built their own LiPo batteries that were square, and every time they had a new car, they had to redesign the entire battery, a huge battery. So what Tesla did is they said, we're not going to reinvent the wheel. We're going to use the existing 18650s and we're just going to put them in series and parallel. So Tesla uses now they converted to 21700 lately. I think that was 2023-ish. So if you look through it, because we only have 15 minutes left, I want at least 10 minutes for the demo. But if you look at it, a single one is 74P 6S. So 6S gives you how many voltage? 24 volts. It's 24 volts. And then there's 74 in parallel. So if each one could take 10 amps, how many amps can 74 in parallel take? 740. So, oops. This one is rated at 500 amps, so it's 750 amps. Okay. So that's actually just the pack, and then the packs of packs. So this is one pack of 74P 6S, so it's 444 batteries, 22.8 volts, and 750 amps. And then the actual car has 16 of those packs. So the total number is 7,104 18650s. And the voltage is 20 volts, and the current is fixed I is 16 times 750 amps. That's a lot of amps. So on next week we're going to do the motor lecture. Wait until you see the transistors they use to use that for their motors. So stay tuned. And of course, there's a obligatory YouTube video that you can watch in the privacy of your own home where they break it down. They show you all the
Isolation issues.
batteries. Okay, they break it down. So tear down. Okay. This is your battery. And so you have 2 cells stacked up and you have your connector coming out. And you have this balance plug, which I'm going to talk about in a minute. Normally you don't need it. All you need is this. This is the high current connector. It goes to your flight controller. And you all have already soldered to the flight controller, hopefully the other end of that. So briefly about connectors, you're using what's called an XT60 connector. That means it's rated for 60 amps. XT90 connectors are related for 90 amps, XT30 connectors are related for 30 amps, etc. There's also Dean's connectors, there's GST connectors, there are lots of kind of connectors. Here's the most common ones used for drones. So getting back to your battery, we've covered this, we've covered this. Now you know what the voltage is, and now you know what 2S1P means. Lithium ion is not as much current. Typically, they can only handle about 10 amps. So your battery can handle 100 amps, but lithium ion can typically handle only about 10. And this is the charging characteristics. Okay, so now how do you charge them? Because I want to do the demo charging. So to charge the battery, as I showed you, it has to be done properly for safety reasons. So you just push current through with a charge circuit, but you don't push it all at once. If you push the current through too fast, you'll create a fire. And if you charge it up to too high of a voltage, you'll create a fire. So it's very important not to charge it too fast. And it's very important not to charge it to too high of a voltage. Rule of thumb, don't charge it if it's fully discharged. Take at least an hour to charge it. So if it's 2.2 amp hour battery that's fully discharged, you're going to have to push 2.2 amps back in for an hour to charge it. Don't exceed that charge current. Okay. And in reality, it's better to initially have a constant charge current and then at the very end have the current gradually go down instead of suddenly. So all this is programmed into your charger. I think we have 3 slides left until we do the demo. Now, these are safer because they have a hard shell. They have 10 amps max instead of 100 amp max, which is not quite good enough for our drones. I think there are some 20 amp versions of the 18650s, and I'd like to go back to them because they're safer. This is just protected with plastic. This has a nice metal casing. So I'd like to go back to these at some point. I just haven't had time to switch the class back. But the normal ones that you buy have only 5 amps of max current. And that's not enough for your drone. And by the way, the cost of these, I forgot what the cost of these are. I think it's like $20 or something. These are between $1 to $10. So you can do the math. And for a Tesla, if you have 7,000 batteries, you can do the math. That's how much your battery for the Tesla is going to cost. Yeah. Not something to sneeze at. Okay. The balance lead is there for 2 reasons. One is to read out the cells, and the other is to read out the cells. So yeah, you just want to know what each individual cell is doing sometimes to make sure that everything is correct. If the cells are out of balance, if one's a really high voltage, one's a really low voltage, that's a damaged battery. You should probably not use it. So they should all be about the same voltage. And when you charge it, you can actually force them all to have the same voltage. So you have a balance lead here. They're JST XH connector types. And if you have a 2S battery, there'll be 3 leads: ground, the positive voltage of the first cell, and then the next cell, and so on. And 6X is about the most people usually do with drones. Even Tesla is a 6S. They don't go higher. And then we have the battery checker and the demo. So there is a YouTube video here that also is linked that has a tutorial. And now you're going to get the Peter Burke 10-minute tutorial of how to charge the battery.